All right, we'll go ahead and get started. There'll probably be a couple more people trickling in, so please, Christina and other project leads, watch for that and admit them as they come in. Awesome, but thank you everyone for being here today. We're really excited to show off our PPR. Now this is a little different than previous years just because of the nature of what this design cycle looks like, and we'll go into that a little bit further. So first off, the scope of this review is design decisions, preliminary designs, and early analysis for projects and or R&D projects. So the project slides will be presented by each project lead, as well as some project members that have worked on these certain components. In terms of questions, you may by all means ask questions during the slides. You can either speak up or raise your hand and we will look for those. You can also ask questions following each project slides. There will be a slide dedicated to questions. And also there'll be one more chance at the end of this full presentation for any go backs or other questions that you have. The presenting order for today is Nosecone, then Recovery Coupler, Payload Coupler, Airframes, fins, parachutes, Nosecone Ejection, and finally parachute stage separator. All right, and the last little bit of information before we start is that it is different than previous years. As I spoke about, we have differentiated between a typical preliminary design review and also added in a project progress report. And so each project has chosen either to focus on a preliminary design review or show off a project progress report in which they will display what they have worked on in terms of R&D progress, or just what they have improved since last year on their main projects. And some of these projects have chosen to do a little bit of both. So you'll see that as we go forward. All right, and so lastly, the reason that we're doing this is, as I said, because of the nature of the shift from a manufacturing focus based on where everything ended up last year and the start of this year where we're kind of more focused on R&D and project rescoping. So that's why we're kind of focusing on a little bit different of a scope for this PDR. Okay, so starting off is Nosecone with Brandon.
Thank you, Zach. So I'm Brandon Shear, the Nosecone project lead. And today we'll be doing a combination of a PDR and a PPR. Alongside me presenting today will be Karina Bridgman, Kyle Shayer, and Ignacio Ray. Ignacio, I apologize for the typo. Next slide, please. So I'll give you a little project overview of the Nosecone project. Some of these are redundant in the sense that we had already covered these last year, but I'm going to cover them again just for the sake of the new members. So some design considerations the Nosecone project has to make is withstanding aerodynamic and inertial forces during flight. So we're going about Mach 1.2 and accelerating at about 10 Gs. So those forces are not negligible. Another thing we have to consider is the payload structure. This year it is within the Nosecone as opposed to external attachment. And lastly, we have to consider the pressure-induced stresses and shock forces during ejection. And this is new given the fact that we have to eject our Nosecone to deploy the payload. Some IREC rules we have to abide by are RF transparency, hence the use of fiberglass. We have to design with a minimum factor of safety of 2 with regards to yielding, and our part has to be structurally integral. And some integration requirements for integrating with Payload Coupler. We need to integrate a 1-inch sleeve. That way we can bolt the two together. And new to this year is creating a tether line between the Nosecone and the Payload Coupler. That way we can recover Nosecone per IREC requirements. Next slide, please. So our current goals, we'll start with the goals as of last year, which remain current. We want to minimize form drag, and we've done this by optimizing our geometry in OpenRocket. We also want to mitigate the weight. So instead of building the Nosecone out of aluminum, we chose composites. In our case, we chose fiberglass. We also want to optimize the structural safety. So we apply a factor of safety of 3 to all of our calculations, just because we're dealing with composites, and the nature of composites is very unpredictable without the proper tools on hand. And also we want to house the payload. So for 2020, we have some new goals on top of these 2019 to current goals. We want to safely eject the nosecone from the payload coupler. That will be achieved with nosecone ejection systems, which I will talk about shortly. We also want to recover the nosecone. This will also be covered in a bit. And lastly, this is a repetition of before, but we do want to house the payload. But this year, the payload has changed from in case you're unfamiliar with last year's payload, it was a ceramic plate which actuated plasma around the circumference of the nosecone with the goal of reducing the overall drag by increasing the length of laminar flow over the rocket. So if you look at this diagram on the right, you can see those indents or that negative space on the nosecone. That's where the ceramic plates for the plasma actuators would have been. But we are moving away from that, and the payload will be internal, so inside the nosecone. So we are also including that consideration as part of our rescope. And we will do so by filling those payload inserts with fiberglass, doing a wet layup or prepreg, whatever we have on hand. Next slide, please. So we'll start with doing some of the rescope research that the team has conducted. Next slide, please. So the first design change, or addition rather, that we made is the nosecone being ejected, hence NCE, nosecone ejection. So some things we have to consider during the ejection are the internal pressure forces, because the nosecone will be a pressure vessel. So we can't just kind of, hope that the nosecone will not shatter into smithereens. So we have to design for those internal pressure forces during ejection, as well as making sure the bolt holes are strong enough to break the breakaway bolts that will be connecting payload coupler to nosecone. And you can see I have some free body diagrams, very simple, some things that aren't included, just because at apogee, we can neglect gravity. It's very minimal. That won't affect our calculations too much. And also aerodynamic drag. We may consider that, or we will consider that actually in our further FEA simulations, just to account for the unlikely scenario that we deploy prematurely and we are experiencing significant aerodynamic drag. So yeah, and also we have to account for the force of the bolt on the bolt holes. So in other words, when we eject the nosecone, the bolt holes will be opposing the force of the bolt, and we need to make sure those bolt holes are stronger than the bolts themselves, so the bolts break and the nosecone ejects. All right, next slide, please. So some more constraints. Now we're moving on to the recovery section. So this entails the tether between nosecone and payload coupler in order to make it recoverable. So something we have to consider with that is how we assemble this. And so we will use a tether assembly, essentially tethering the nosecone to the payload coupler with an elastic cord. And we must design that such that it withstands the shock force on nosecone deployment. Also, we need to accommodate the internal space for the payload. I think typically, or what they told us was 3-stack CubeSat size, and we are well within those margins. So other environmental loading conditions, you can see on the left, first of all, I said the force of gravity vector is unknown just because we don't know the orientation of the nosecone at nosecone deployment. So we don't know in what direction this force is going to act. Two things we do know for sure is when the nosecone deploys, we will have a shock force exerted on that tether. You can see the eye bolt right there. I'll go into greater detail on this schematic later, or this diagram later, explaining how this works, and we'll have the force of the cone acting in the opposite direction. Now I'd like to explain this, and also on the bottom of the page, you can see how I calculated those forces. The shock cord was, or the shock force was actually given to me by Catherine Butler on parachutes and Nosecone ejection. So if you have any questions about that equation specifically, go ahead and refer to her. All right, next slide, please. Okay, yeah, and so in order to integrate with Payload Coupler, we will be using, and I apologize that the CAD does not reflect this. We just determined this today, but we will be using 5 breakaway bolts instead of 4. And also, in order to recover the Nosecone, we will have to be tethered to the Payload Coupler. So we will connect that tether line at the eye bolt on the forward of the Nosecone, and some fastener on the forward face of the Payload Coupler. Now, integrating with Nosecone ejection, the only design we have to, or design requirement we need to make really, is ensuring that the Nosecone will withstand those pressure forces, as well as this isn't one of the bullet points, but it should be. Also make sure that the Nosecone, the bolt holes on the Nosecone won't break or fail on ejection. And now for external interfaces, so members of other sub-teams, we will be integrating heavily with Payload. We want to ensure that the Nosecone in no way will inhibit the deployment of the payload, and also ensure that we will house them with the proper size accommodations. Next slide, please. So the first, really the main concept we had explored was the eye bolt tip plug combination. So if you look at this diagram, you can see on that left, we have the dark gray. That will be the tip. That is on, of course, the tip of the Nosecone. And inside the Nosecone, you can see on the right that that lighter gray is the Nosecone plug, which will be either resin printed or machined from aluminum. And you can see it's obvious, but the eye bolt's there. And on the outside, towards the bottom and surrounding the plug, we have the Nosecone surface. And how this works, or actually we'll get into that later. But that's essentially the gist of the system, and some of its benefits include the eye bolt being able to double as a tether point plus a plug tip fastener. So essentially, it will ensure that not only the tip and the plug stay in place, but also it will secure the tether line between Nosecone and Payload Coupler. And this will exert a force from the eye bolt to the threads of the tip, and then to the top face of the Nosecone, which is really important to us because that means we don't have to rely on the frictional forces due to adhesion or friction fitting of the Nosecone plug. Instead, we will rely on the normal forces exerted between the Nosecone and the tip because they are interfaced together. And then one of the trade-offs we actually had with this design, and we couldn't really find a workaround, is integrating our AMD, or the airspeed measurement device, maybe more commonly known as a Pitot tube. That was one of the R&D projects we had lined up for this year, but it looks like that'll be a more long-term R&D project. Cool. Next slide, please. So this is, again, I've briefly demonstrated how the load path is designed, but you can see here at the interface on the middle top between the cone and the tip, that's where we will be exerting our most of the shock forces, and those will be transmitted from the tip to the Nosecone. And yeah, and we have our bolt here. That's 3/8 inch, 20 thread per inch carbon steel bolt. And yeah, next slide, please. Cool. And we did some analysis on the shock forces using the von Mises criteria, which is less conservative, but which is good in our case because it allows for us to design a lighter part. So we're not, I guess, over designing. And some of the assumptions we made during our Ansys stress analysis, FEA stress analysis, we assumed that the plug and bolts were one part. This was partially due to, just for the sake of simplicity, it's very difficult, we learned, to model threads in, or rather thread face interfaces in Ansys. We end up reaching our node limit. So we had to simplify things for the meantime. So eventually we will be doing analysis with threads once we can figure out how to either minimize the number of nodes, or we can get access to a license that will allow us to perform an analysis with more nodes. Some boundary conditions. There was really only one boundary condition, and that was the bottom circumference of the nose cone being fixed against translation. This is a very conservative assumption as well, because we don't actually calculate the acceleration of the nose cone, because that is what is acting against the tip. So, and that is also, again, we don't know the situation or the scenario, the conditions at apogee, so we don't know which way the nose cone will be moving or anything. So we just essentially put a fixed, a fixed support at the base of the nose cone to sort of simulate the acceleration of the nose cone, or the force of the nose cone onto the tip. And when we ran these simulations, we got a factor of safety of about 20, or a safety margin of 19, which is well within margin. Yeah, and and at the bottom you can see the mesh that we made. It's triangular, but in reality, or we would desire to make a hex mesh, or a hex dominant mesh with quadrilaterals, but we were having some issues designing that mesh. So next slide, please. Here, this is looking at the bottom of the nose cone. Now, if you look at the circumference, that very thin face right there, that's where we put our fixed support. And if you look down the middle there, you can see a hex bolt. It's a simplified version of our eye bolt. We applied the force on that face. And that green right there, that is the plug. And something you can't see in this is the interface between the bolt and the plug and the tip. That is, there are no threads there, as I had mentioned. It's essentially treating the whole thing, the bolt, tip, and plug interface, as one part, one solid part. We will move on now. Cool, and it's kind of difficult to see here, but we've applied the shock force that we calculated earlier. That point A, that's that red arrow on the left, facing away from the tip, as it would during actual flight conditions. And we have the fixed support at point B. You can see that very dim. And those are the loading conditions we had applied during our analysis. Next slide, please. Cool. And then these simulations actually yielded, like I said, very desirable margins of safety, with the max strain being 484.98 microstrain, and the stress being 1066 psi. And next slide, please. And then the last thing we'll be doing in order to account for in preparation for the recovery portion of our project is testing with Payload Coupler, Nosecone, and potentially Payload. We will use a camera to determine the optimal delay between fuses between Payload Coupler and Nosecone for a given payload ejection method. Now, this will depend on the ejection method we use, and that is currently under deliberation between payload and structures. And lastly, after we do that, after we prove that our concept works, we will be doing a full recovery system testing. And yeah, next slide, please. Cool. Now I will hand it off to Karina Bridgman, who will be presenting the, as well as Kyle Scher, they will be presenting the R&D we performed on the Resin Infusion manufacturing method.
Hello. So we're going to be doing the resin infusion method for our first research and development. Next slide, please. So for the resin infusion, this is one of the methods to fabricate the nose cone that we used last year. So some of the benefits is that this increases the strength to weight ratio, so we can get that higher apogee, which is what we want, one of the goals. And we also get a more efficient material usage, which then is a decreased cost, which is also very much wanted for manufacturing the nose cone. Some of the trade-offs though is it's hard to predict the resin flow coverage. And then the trial and error with this does cost money, as the resin, when it flows over the nose cone, can be hard to predict, like where it's going to go and how much it's going to cover the fiberglass and such. And then there's a photo of one of the female molds that we used for our current manufacturing plan. Next slide, please. So the first concept for how to resin infuse the nose cone this year is to do a horizontally integrated halves. So as you can see on the right, the red line will be where you would cut the nose cone. So do 2 halves and put the seams in the longitudinal direction. So this is going to be safer as you get a lower longitudinal stress, and you're going to get a less seam area, which will then minimize the weight as there'll be less prepreg in the seams and the inside. Some of the trade-offs though is when cutting it at this angle, it's going to be hard to manufacture the exact circumference of both halves. And it's very important to get this so that the nose cone is one solid piece in the end. So it's difficult to execute. So that's one of the trade-offs. Next slide, please. The next concept of how to resin infuse it will be a seam down the opposite side, so doing 2 different halves, which is how we did it last year. So we already have 1 half of the nose cone. So this is going to be most likely how we were going to be resin infusing the nose cone this year, as we can then put the 2 halves together since we already have 1. So then this is going to ensure that the entire nose cone is in place. We will have more seams along the middles, which will increase the weight a little bit, but in the end, it's going to be able to keep the nose cone as its entire piece. Yeah. Next slide, please.
Cool. And now Kyle Scher will present the next portion of this R&D project. Thanks, Karina.
All right, so this is the resin infusion for the nose cone. So basically, pretty much everything will be in the composite shop this year. Well, not this year, but with the exception of the circular retainers. And I will go into more depth about those in a couple slides. The mold is the same one we had from last year, which was made at Northwind Composites. And so what we're going to do is lay the carbon fiber or the fiberglass plies on top of this mold using the 0-90-45 orientation. And then we will bag the nose cone using a vacuum bag. And then this will be sealed with monkey tape. And this prevents any air from getting out during the vacuum process. Then the vacuum pump will be connected with around 2 to 3 resin lines to draw the resin into the nose cone. And then the last step for that is the nose cone will then be cured according to the data sheet. And for the female mold, we also will resin infuse that. And that's obvious. That's what we had before, the one we're using from Northwind. Similar process. The only difference is that we are going to be putting the plies onto the male plug. All right, next slide. So yeah, here's that mold from Northwind. As you can see on the left, and that's where the plies would go down the center. Next slide, please. And then here's a more in-depth look at the resin infusion process. In this case, this was the mold being made at Northwind. So starting from the left, we have the Resin Reservoirs. So in the little red solo cup there, it's in cold water. And the purpose of this is to prevent the resin from solidifying. And then you have connected to that the resin feed lines, which go up towards where the mold is being made. And then right above the text box there on the bottom, you can see the clamp, and this controls the resin flow. And then the bagging setup, you can see there in the red, that's where all the plies are. In this case, it was fiberglass for the fiber material. And as you can see, the resin spreads out up top, and what's supposed to happen is it goes through all the different layers kind of at the same time. And then on the right, bottom right, we have the high density foam male plug, and that's what gives the shape of the mold. Next slide, please. So these are the circular retainers that I mentioned earlier. You have one on the base, in the middle, and then the tip of the nose cone. And they're basically these metal rings that go around the outside of the cone. And this happens during the curing process, and it prevents any eccentricity in the diameter, which in other words just means that we're trying to keep it circular and keep it from warping during the process. All right, next slide, please. All right, lastly, we have machinery and pricing. So we're going to be using the CNC fabric cutter, the autoclave, the oven, and the vacuum pump. And these are all located in the composite shop. And we'll need about 2 to 3 project members working on this at one time. And in terms of pricing, the composite shop, everything there, all the machinery is free to use. So we don't have to worry about that, which is nice. And material pricing will be listed near the end of the presentation. So.
Cool, thank you, Kyle. And now Ignacio Ray will be presenting our R&D for the airspeed measurement device.
All right, awesome. Let's get started with the next slide. All right, so this is our extent of research for the AMD, which stands for the Airspeed Measurement Device. And so essentially integrating an airspeed measurement device will provide valuable data regarding the rocket's velocity and acceleration during flight. So right away, we have some clear benefits. Kind of what I said before, it provides clear data on the rocket flight acceleration. We can find the max velocity and the time of apogee from this. The second point is that it gives us opportunity to have live data from the rocket, which could assist in different staging procedures. For example, it could provide us the proper, like a precise time for when we want to eject the nose cone from the actual rocket itself. Going into trade-offs, an AMD, it has a possibility for being difficult to manufacture just because it's a tube, has a very long hole in it, and it'll require a lot of research in order to manufacture this. And the second thing is that it requires consistent coordination with other sub-teams. This is primarily with avionics, just to ensure that all the electronic systems are properly calibrated with the Pitot, with the AMD itself, and to get data from that. Just some things that we kind of got to note is that at supersonic speeds, shock waves may cause a margin of error between our measured pressures and velocity from the AMD and our actual values. And I think around 0.3, compressibility effects may start to influence our measured values. And we need further analysis in order to compute exactly how significant these errors could be. Next slide. All right, so for our loads and constraints, the first is electronic systems. For example, the pressure transducer, as you can see on the figure on the right, it's what basically calculates the difference between the total pressure and the static pressure. This has to be accommodated inside the nose cone. And so this requires heavy integration with avionics. The second thing, this is also directly from avionics. We need an excitation voltage of 5 volts in order to get the AMD to work. Moving on to the environmental and loading conditions. Externally, the AMD will experience body forces from the rocket in one direction, and on the other side, we'll be experiencing air drag and gravity. And internally, inside the AMD, there'll be different pressure conditions coming from the total dynamic and static pressures. This is just all from the fluids moving inside of them. Next slide. All right, so we have 2 main concepts for the AMD. The first one being just a pitot tube. Essentially what a pitot tube is. On the figure on the right, you can see that there is a dynamic pressure port. Just like the title says, it records dynamic pressure. A static pressure port is also included, but not on the pitot tube itself. It will be located on a different part of the rocket, such as like the airframes or something like that. And so the design benefits from this is that once we get this manufactured or bought, the pitot tube setup is relatively easy. And the second thing is that the static port measurements will have negligible error due to its distance away from supersonic flight effects, the nose cone. Essentially what this means is since the static port is not located directly on the pitot tube and further away, it won't be subject to all these supersonic shockwave effects that the pitot tube will experience directly at the tip of the nose cone. For trade-offs, this will require a lot of coordination with other project teams to get a static port somehow integrated in with their design. And so this will require a lot of teamwork and movement with that. And the second thing, in order to integrate a pressure transducer to receive data from both pressure ports, this may be a little bit complicated considering that the dynamic pressure port and the static pressure port would be in different locations entirely. And so this could complicate things in order to decide where we're going to have the pressure transducer and how we set up those electronics. And next slide. All right, so for our second concept for the AMD, this is the pitot static tube. And the main difference between the pitot static tube and the pitot tube is that the static pressure port is located on the pitot static tube itself, as you can see on the figure on the right. And so some benefits from this, both ports will be on the same tube. This itself, it creates a more compact device, leading into our second benefit, which is that the pressure transducer can easily read the pressures just because of the proximity with each other. And with the trade-offs, this would be harder to manufacture. Pitot tubes themselves could be difficult to manufacture, but considering that the static pressure port is also going to be needed on this pitot static tube, that requires a kind of another layer to consider for manufacturing. And the second thing, which is the most important thing and the hardest thing that we've had with developing, is shock waves. Shock waves on the tip of the tube could impact our static port placement, and we need more design analysis in order to compute exactly where we want to have this. And so I'll kind of talk about this on the next slide. All right, so starting off, to do any of these analysis for like pitot tube, shock waves, all this, it's pretty difficult to do it by hand, considering the geometry of the nose cone and the AMD. And so we will require the use of computational fluid dynamics, CFD. This is just to determine exact shockwave values and where the static port is going to be placed. And in terms of assumptions, the first one is just the atmospheric conditions at the IREC launch location, which should be approximately 93 degrees Fahrenheit and just about 26 inches of mercury. The second assumption we have is that since the nose cone is considered a blunt body, we expect to get a detached normal shock wave. And so we have to account for that when determining the static port placement. And the third thing, the margin of error, as you can see on the figure on the right, it kind of shows you the differences in pressures due to supersonic effects. Since the rocket's only going up to about 1.2, maybe 1.3 Mach, we believe that these pressure differences may be minimal, but again, we need to confirm this with faculty just because fluids is just a whole another thing, very, very difficult to understand. And so we just want to make sure that we talk to, people who are more experienced in this. And then again, pressure margin of error also determined from this graph on the right. We think it's going to be about 5 to 7%, but again, want to confirm with faculty. Next slide. All right, and so coming down into manufacturing. So it's kind of this big thing where whether we want to manufacture the AMD itself or buy it off of a third party. As of now, we believe that manufacturing it ourselves is going to be the best route since we want it to be fitted exactly for our nose cone. And in terms of actually how we're going to be manufacturing it and the methods to do this, we're still kind of weighing our options on this. And next slide.
Cool, thank you, Ignacio. So I'll finish up this presentation. This is just our list of materials and components. So Zach, you can skip 2 slides to cost analysis. Cool. So cost analysis, this is more than we've spent in previous years, 60502. Now this is mostly due in part to the fact that We will have to purchase quite a bit of new hardware for manufacturing using Resin Infusion method, but in the long term, this will definitely be a benefit for us, given we will have lower weight, higher strength, and these parts, specifically the tools we will use or that we'll have to purchase, can be reused throughout the years. Next slide. And this is our schedule, which is, I'm sure you can imagine, very volatile. So this will be subject to change, but kind of the big thing on our list right now is getting some more comprehensive analysis done. And we hope to get that done around the first week of winter quarter. All right, next slide, please. So next steps for us moving forward, a few deliverables we have include improving the mesh for all of our FEA sims. So we want to incorporate a hex dominant mesh into our sims. And we also want to learn how to use ACP, which is Ansys's composite post. I forgot the acronym, but it's the Ansys composite feature, which will give us far more accurate results for our simulations. And we don't have to use such a high factor of safety because we can anticipate having more accurate simulation results. Another thing we are doing right now actually is modeling seam strength for our pressure vessel analysis. We are currently looking into how to measure the seam strength between our nose cone and the matrix of the seams, given that they will be two separate materials and not cured together initially. So we are finding out how to model that. We are talking to faculty, and they're helping us out quite a bit. Also, and if we do learn from this that the seams aren't strong enough, we will then redesign them. And then also we want to get a nose cone manufactured so we can integrate and test and maybe launch one day. We'll see about that. And then some big goals, just general goals for the nose cone team for the rest of the year is to manufacture 2 cones, one using prepreg. We already have half a cone made out of prepreg, so now we just got to make the other half. And the second one being built using Resin Infusion. And in order to do that, we will first have to make some Resin Infusion work orders so that we have a comprehensive step-by-step plan on how we plan on manufacturing that can also be passed down to future generations of SARP. Next slide. Does anyone have any questions? No questions. All right. Next slide then. I will hand it off to the Honorable Greg Boyce from Recovery Coupler.
Thanks, Brandon. My name is Greg Boyce. I'm the Recovery Coupler project lead, and we're going to be having a mix of a PPR and PDR here. Joining me in presenting is going to be Aiden Vandenberg, Vincent Zhao, and Tyler Holloway. Go ahead, Zach. All right, for an overview of the project, we operate on an internal factor of safety of greater than 2 and a buckling factor of safety of greater than 20, just due to the strange nature of the buckling happening on our coupler. We try to be really conservative because we don't really know what's going to happen in flight. Also, we need RF transparent doors so that our avionics systems can work well in flight. The function of the recovery coupler is to be a hard point for the main parachute in the recovery system. That could be Aries, it could be the normal chute, whatever happens, we want to be ready for that. We also have to house any of the recovery electronics and avionics electronics, as well as recovery ejection components. And the goal is here to reduce weight via optimizing our geometry and introduce more composites this year and next year, hopefully. We also want to have realistic and repeatable manufacturing requirements so that we don't spend all year in the shop. Next slide, please. All right, for loads and constraints on the bulkhead, we're going to have a main parachute tensile shock load of about 2,100 pounds. This would be for Aries, which is the greater of the 2 shock loads. So we just opted to go for the higher one so that no matter what they ended up doing, we could swap it in. And as for the cage, we have a compressive force from the weight acceleration and drag coming up to about 600 pounds. Then in the cage, the column buckling is the main concern. In terms of constraints, at the front of our bulkhead, we have the sleeve bolted to the parachute base shroud, and at the bottom, we have the pressure and tank connection connecting to the pressure and tank, as it says. Internally, we also have to have room for all of our components that we're putting inside of there, which happened to be one of our biggest problems this year, but we made it happen. All right, go ahead. In terms of research, one thing we did is we had some of our new members spend a lot of time learning of the new programs we have. I'm going to have them talk a little bit about what they've been doing. And we've also been researching the composite coupler a lot. The composite coupler offers a lot of weight savings, but it's also really difficult to manufacture, and we don't feel super confident with analysis yet. We're going to try to change that this year and next year. And following up from the composite coupler, we want to learn how we can more effectively bond composites. So we investigated some of the different methods available right now, and I'll have Vincent talk about that. We also investigated pre versus post-processing methods, specifically in terms of the cage for cutting the door holes. So I'll have Aiden talk more about that. And in terms of the composite coupler, I also went a little bit into a more advanced composite coupler because we need a next step, assuming we implement this in the next year or the year after. So I took the liberty of just designing something really quickly, and hopefully we research that a bit more later in the year. You can go ahead to the next. I'll pass that on to Tyler.
All right. So the new members of the recovery coupler have spent time coming up to speed on the programs that we are going to be using for analysis and design. Some of us haven't ever seen SolidWorks before, so we spent a lot of time doing basic part design and tutorials and whatnot. And then we started looking at Ansys for some FEA, including static structural and ACP, as we're looking at doing some composite materials. And then overall, we're looking at rocketry and really taking a lot of time looking at the GrabCAD for the current design and trying to figure out what it looks like, how everything fits together, and how what possible things could be done in the future when we might have lead. Next slide, please.
All right, thank you, Tyler. I'll take over for this one. I'm going to talk a little bit about the composite coupler that we have right now. There was actually a composite coupler designed by the 2020 senior capstone team, namely Cody Olson. He kind of took charge of that one. But basically, it aims to incorporate composites into the recovery coupler because we never have before. So hopefully it'll add a lot of weight savings. It's just made up of kind of the typical components of the existing coupler with a composite cage versus an aluminum cage, and then a mixed composite aluminum and a hex core bulkhead. That's a pretty complicated part, but it's really cool design. And then also just the same aluminum pressure and tank connection. We could also investigate turning that into carbon later, but that's less of an important piece right now. We want to focus on the main components. Go ahead and go to the next one. So they actually did some analysis last year using Ansys ACP, so this is pretty reliable stuff. Thank you, Cody, for this. The face sheet factor of safety between the top and bottom face sheets was about 1.3 to 1.6, so not quite to our 2 that we're looking for. But keep in mind, this is a pretty accurate analysis because they did use the composites analysis tool. So it'd be pretty easy to up that a little bit with a few extra layers and make it work. The wagon wheel, as they call it, is the aluminum insert in the bulkhead, and that had a factor of safety of 2.25. And that's a very reliable one because it's aluminum, we're used to that. And cage tension had a factor of safety of 4.54 from the parachute load, and compression had a factor of safety of almost 30. So we're good on buckling if we use the composite coupler. And altogether, it ended up saving 30% of the weight of the coupler. So it's something really worth pursuing in this year or the next year if we get around to it. But we still need to do a little bit of research for it. And as I talked about, we're looking into bonding methods, how we're going to manufacture the cage, and we're looking into learning Ansys ACP ourselves so we can feel confident making changes to this wherever necessary, or developing a better one later on. Go ahead. I'll pass it off to Vincent for this one.
All right, hey guys, I'm Vincent from Recovery Coupler team, and I'll be introducing bonding methods. So here are 3 current bonding methods that we investigated: bolt joint, adhesive joint, and film adhesive with Prepregs. So for the first 2 joint method, it's mainly used on aluminum and carbon fiber composite parts. As for bolt joint, it's basically just using bolts to connect 2 parts. It's pretty cheap, pretty easily attainable, but we need to consider effect of drilling on parts on the composite part because if we drill holes on the composite materials, it might influence the bonding strengths, which is not what we want. So we might not pick this joint methods, and we will introduce adhesive joint with two industrial used adhesives for composite parts, epoxy and polyurethane. The difference between them is that for epoxy, it has higher thermal stability, but lower toughness. For polyurethane, it has higher toughness, but lower bonding strength and thermal stability. And so as for the rocket environment, it's pretty high temperature. So we are gonna use epoxy as our basic adhesive. But with solving the problem of lower toughness, we are going to use rubber modified epoxy. There's a typo in that. It's not joint, it's epoxy. ATBN and CTBN, and these two are abbreviations for two types of rubber materials. By adding them into the epoxy, the final adhesive will have higher toughness than the unmodified epoxy. But if we use only single rubber in that epoxy, it might weaken the bonding properties like heat resistance. So in the future, we are gonna do more research on the proportion between rubbers adding into the epoxy adhesive. The third one, film adhesive with Prepregs. It is especially for aramid honeycomb core bulkhead. It is unique because it uses a sandwich structure. So basically it means honeycomb core in the middle with the top and bottom side for the film adhesive. And finally, the outside is the prepreg. And the whole assembly will use in curing process, and the resin inside the film adhesive will melt and flows to create bonds between prepregs and the honeycomb. Next slide, please. Yeah, so here's our conclusions on the bonding methods. So for aluminum and carbon fiber parts, we are going to use rubber modified epoxy because their improved toughness, good bonding strength with epoxy on metal substrate, and also high thermal stability. So at the left bottom side, the table is research data for bonding properties for rubber modified epoxy. And as we can see, the last column, the modified epoxy with adding some rubber has significant higher toughness than the unmodified one. So for the honeycomb core bulkhead, we are going to use the resin film adhesive just for the sandwich structure. Yeah. Next slide.
All right, thank you, Vincent. I'll pass it now along to Aiden for pre versus post process.
All right, so I'm going to go over the research we did for our pre versus post processing. And the question we wanted to answer was which method of composite manufacturing is best for our recovery couplers composite cage doors. And we did some research into common industry methods. And as you can see here, these are the main ones I found, and they were closed molding, which is good adhesion and improves mechanical properties, but it's very expensive. And the expensive part, you're going to see a lot. That is the case for most of these. The next one's compression molding, which is fast molding cycles, high design flexibility, yet the molds are also very expensive. That's the most interesting one to me because it would lead to probably the least amount of post-processing we need. But again, the molds are extremely expensive and probably out of the scope of the SARP's budget, unfortunately. And the next one's reinforced reaction injecting molding, which is fast cycle time, low labor, strength improved, and yet it's very rare and also expensive. And then centrifugal casting is good for hollow parts like ours, simple and cheap, but it requires pretty much the same, if not more, amount of post-processing than the last one, which is the one we're used to, which is a prepreg layup. Simple, cheap, feasible, but most post-processing required. So next slide, please. And so the conclusions is pretty much what we've determined in the last few years, which is the post-processing is most feasible for SARP due to our budget limitations. We've used it before, not in this case, but and it's the cheapest option, obviously. Pre-processing requires less machining, but it's way too expensive and out of our scope for now. But it's worth keeping note of these processes because we could possibly pursue them in the future. And also the industry standard is mostly post-processing based, just because of the limitations of the technology we have right now, causes most companies to use methods similar to the one we chose. And next slide, please. And I'll pass it back over to Greg.
Thanks, Aiden. All right, now I'm going to talk briefly about the advanced composite coupler. This is just kind of a logical next step if we do manage to rein in the composite coupler that we have right now. So as you can see, it's a really rough design. I just kind of came up with this one day on a whim and just thought it out a little bit. But basically what it is, it's one connected piece of carbon fiber instead of two separate parts. And so it'll use aluminum 3D printed and aramid core inserts, just kind of similar to the existing carbon coupler design. But it'll be built on a filleted mandrel, as well as using that insert on top with a vacuum bag situation going on there. It's very much in its infancy. If anyone has more questions on it, I'd be happy to talk about it later, but that's all I have for that right now. All right, so in terms of what we're moving forward with this year, we unfortunately have come to the conclusion that the aluminum coupler will fly this year if we do end up flying the rocket. The reason being lack of shop time, and we honestly don't really know how to analyze very well. So I don't feel comfortable putting a part out just yet without doing some of my own analysis, as much as I trust Cody. So the steps to be taken to progress the composite coupler will continue. We'll keep researching. We'll try to learn how to do ACP a bit better. And hopefully we can look into some more advanced methods too, not just the design that already exists. And we may even try to manufacture something if we do get some spare time and we do end up getting into the shops. Go ahead. All right, now into the coupler that we all know and love. I'm just going to run through this briefly because this is really similar to the PDR/CDR we had last year, but for those of you that weren't here, I will run through it. This is the design that we're going to use this year if we do fly. So our concepts start with the bulkhead. The design benefits, it's really easy to manufacture. We just need a lathe and a mill. It doesn't take too long. We're almost done with it already. It has a successful history. It's just kind of a variation of ones we've already flown and won competitions with. The bowl feature distributes the load really well, so it's allowed us to reduce the weight a little bit. And there's a weld chamfer, so it's easy for post-processing. Some of the trade-offs, it's aluminum, so it's still heavy. We haven't turned it into composites, and it requires a weld, so we have to hire somebody. Next is the cage, which integrates with the bulkhead. The design benefits here, it's tried and tested. Again, we've won competitions with this design. We've already almost finished manufacturing it, and it's really easy to manufacture. It's just a lathe feature, and then you put it over onto the mill and you put those holes in it. And then one other benefit is it's a bit shorter than previous years, so it can handle buckling a little bit better, and in turn we could save a bit more weight. Trade-offs again, it's aluminum. It's kind of heavy, and it requires some welding again. But go ahead. Next, parachute base sleeve. Super simple part. Could probably machine it in a day if we had to. It's going to be full welded to the bulkhead. It's essentially just a aluminum tube with 4 holes in it, and it integrates with the parachute bay. And the design trade-offs here, it's not very optimized. We could probably make it better, and that's something I've been thinking about doing a little bit later if we have time. And again, it's aluminum. This is actually a part I think we could try to do something with composites even this year due to the simplicity of the design, but we haven't talked about that yet. All right, go ahead. Next, the pressure tank connector, probably the coolest looking part in my opinion. Design benefits, it's fairly easy to manufacture. It's just lathe features, and then you put it on the mill with a little rotating head, and you mill out all the features around the circumference. It's pretty weight optimized. I think we could go a bit further, but it's saved a lot of weight with those cutouts. Design trade-offs, still using aluminum. It's not fancy carbon yet. And some of the holes on here may require post-processing in terms of tapping. So that's something to consider, put a little bit of extra time onto our manufacturing. Next is the eyeball, which is what the recovery system integrates with. This is what's going to distribute the load through the bulkhead. The design benefits, it's an off-the-shelf option, so we just purchase it and we're done. We don't have to manufacture anything. Design trade-offs, heavy, it's steel, and it is purchased, so it's not as fun. We don't get to make something. But next. The doors in the door ring. So basically what this is just 3 doors to make sure we are aerodynamically sound in our flight, but it allows people to easily access anything within the coupler, which this year is a lot of things. It's really easy to make. It's just PETG filament that's printed. It should be RF transparent. We were going to do a little bit of testing last year, but we never got around to it. And it's tried and tested. This was on the rocket that won the competition. The design trade-offs, plastic. So we probably have to make new ones every year. It's not something that they could put on a new rocket if they wanted to. Next. The avionics housing. So this is what holds all of the wonderful avionics electronics and design benefits here. It's also 3D printed, so it shouldn't take too long to make. It's not super expensive to make either, and we already have filament coming in. It provides easy access to the avionics electronics, which is something they've never had before, so that's kind of exciting. They just undo a little thumb screw and pull out whatever they need. Design trade-offs, it's untested. This is our newest component, not something we've had in the past. And it requires a lot of fasteners, as you might be able to see on the assembly there. And it's reflected in the bolt chart, which I didn't include because it is so long due to this part. All right, next. Integration. So in terms of internal interfaces within our team, we have the parachute base sleeve, bulkhead, cage, pressure and tank connection, doors and door ring, and avionics housing, which you all just saw. External interfaces, we have to think of all the things that we're keeping inside of it. So we have a space constraint within our coupler, and we are just about out of room. So if anything changes, that's a problem. And if anyone's here from those teams, please let me know many, many months in advance before you change anything. And in terms of other things, recovery electronics and physical systems all integrate with our recovery coupler, hence the name recovery coupler. Also, avionics is living inside of our coupler this year. That's something pretty new, but we've made it happen. We built them a nice little home in terms of the avionics housing. Go ahead. So this is what it looks like altogether. This doesn't have any of the recovery, or it does have avionics in it, excuse me, but it doesn't have any of the recovery things in here. However, they do fit. Trust me, I spent a lot of time on it last year, but I didn't have time to put them into this assembly. But here we are, has all the fasteners we'll be needing and all the parts together. It's a pretty one. Go ahead and go on to the next one. All right, in terms of analysis, this is all things we did last year, and thankfully, since we haven't changed anything on this, it was all readily available. So this is a pretty thorough analysis. Stress analysis of the parachute tensile loading came out with a fixed constraint on the weld face where it's connected to the cage, and we put an assembly of the eye bolt washer and nut to transfer the load, and the load was applied on the flange of the eye bolt nut. At a factor of safety of 2.13, which is within our range, so it was excellent. It's very light. The next one. All right, this was the cage. We use FEA and Euler buckling analysis on this one, just because buckling is something that is pretty hard to characterize. So we just want to cover all our bases here. We have a nice little MATLAB code that does it for us. Stress analysis on here was used with compressive loading of 604 pounds from the acceleration of the weight of the rocket. Assumptions here, we had a fixed constraint on the bottom of the cage. The assembly was one of the bulkhead and the cage together, fixed together at the weld face. The force was applied at the top of the bulkhead, so to emulate kind of the pressure of the rocket coming down on it. The FEA factor of safety came out to 21.4, and the Euler buckling factor of safety came out to 23.2. So we're well within our range, and it looks good. All right, on to the next. Here we are with the pressure and tank connection. The stress analysis was also done with the tensile loading on the parachute, as we figured that would be the main problem here. I don't think this will have any problem with compression. However, that's probably something we'll look into either way. But it did very well under the tensile loading. We assumed that it had a fixed constraint on the pressure and tank mounting holes where the bolts connect. We had an assembly of the cage and the pressure and tank connector together, and the force was applied on the top of the cage to emulate the shock force of the parachute. We had a factor of safety of 6.38. So even though this was a fairly optimized part, it could go further. So that's something we may look into later in the year. Go ahead. In terms of testing, we'll be doing Instron testing of 1.5 times expected loads using the ME Mechanical Test Lab if all works out. If we're going towards the end of the year, we're not going to put 1.5 times the load on our bulkhead. We're probably just going to let her fly. But vibration testing, something we've never done before, but since we're housing sensitive electronics and stuff this year, is something we'd like to do. we don't really know where we could get that done. And since none of the facilities are open, probably won't happen this year. But it is something we would love to do in the future to make sure all the things we keep inside are nice and safe. All right, go ahead. There's a manufacturing for any of the aluminum components. So that'll be the cage, bulkhead, sleeve, and pressure tank connection. We'll be doing that in the ME machine shop or the space that we have now. So all we need is the lathe in the mill here, along with some fun attachments for them, like an indexing head on the mill. And we've done all this before. We know how it works. I've spent lots of time writing up work orders on them, so we should be able to crank that out in no time, considering we're already started on it. 3D printed components, that'll be the Avionics Housing doors and the door ring. A lot of us have our own 3D printers, so we use those for sure. And then any of the makerspace printers we have access to, we may use as well. And composites, if we get to that, which we probably won't, unfortunately, we'll be using the Composite Shop autoclave or platen press in terms of our face sheets. I think that may be a good option. On to the next. Materials and components. We already have all of our stock. Sweet. We're cheap this year. Fasteners. We had a lot of them. Almost $100 in just fasteners. And we already have one roll of PETG filament, but we'd like to get another one because we think we're going to go through it, especially if any of our prints fail. Composites, we haven't accounted for any of that, although we're pretty cheap this year, so we probably could get away with getting a little bit. And we're usually sponsored on some composites, so hopefully it wouldn't cost us anything either way. Assuming all goes well, we should spend around 125 bucks. The next one, cost analysis, materials, 100 bucks. Weld, I don't know. Heat treat, I also don't know. And testing would probably be free, but I don't know. We'd have to contact people for weld and heat treat, and since we're not even close to that, we haven't bothered to do it. But it usually fits within our budget just fine, so I'm not terribly concerned with it. And we're looking really cheap this year anyway, so I'm not super concerned with the budget. However, I really don't know what our budget's going to look like this year at this point. On to the next. Thanks, Kat. Good to know. So heat treat should be free this year, and it's from Pacific Metallurgical. Thank you, Kat. So there we go. We're super cheap. We don't need to worry about it. And our schedule, PDR, that's today. Did I put the wrong date? Yeah, my bad. Research, we're going to be doing all year. I would love to spend a lot of time on composites and get us pretty familiar with it, especially for you guys that are going to be here after me. I'd love to come back and see you guys flying some pretty composite parts. Manufacturing, hopefully we get to start at the beginning of next quarter in some shape or form, at least 3D printing or something. And if we want any chance of flying this, we should probably be finished by April. Post-processing, that'll be from April to May. Hopefully, I don't really know how long that's going to take. Testing shouldn't take very long if we have the facility, so I put about 15 days there. And integration, we could do that really fast, but assuming we get things done in the right amount of time, we should have no problem doing it in 2 or 3 weeks. And this is all very to be determined, so take this all with a grain of salt. On to the next. All right, next steps. We need to make sure our aluminum coupler is looking good, which right now it is. We have updated our assemblies. Everything is in order. We have all of our fasteners from McMaster in CAD, all in there looking good. So we're ready to pull the trigger on this coupler at any point in time. We'd also really want to do our analysis on the composite coupler. So that's something we're going to focus on in terms of research, is learning Ansys ACP and throwing some fun parts in there and seeing if we can develop anything really cool. Lastly, we got to manufacture this baby. I'd love to see her fly. And that's it for me. Any questions? All right, awesome. And next is Payload Coupler with the lovely Alex Holden.
Hey. So we'll be going through mostly PDR today with just a very light sprinkling of a project progress report at the very end as kind of our next steps. And Eamon Haugen is going to be presenting the PDR for us, and I will be covering the project report at the end. So take it away, Eamon.
All right, thank you, Alex. So here's Payload Coupler's basic project overview. We have some requirements we'd like to meet, such as supporting a payload of at least 8.8 pounds, We also want to withstand the stresses of the rocket with the factor of safety of 2.0 or greater. And this will come up a little later in our presentation. You'll see why. So the function of the payload coupler is to provide a stiff couple between the upper body tube, which is below us, and the nose cone above us. We also want to secure the payload within the nose cone during the ascent. Some major goals this year, obviously we'd like to have no failure. And then we want simple and repeatable manufacturing that we can hand down to next year's payload coupler team. And then the biggest goal we've had is to be lighter than last year. And so that's been our main research. Next slide, please. And then, so with this research, we've been talking about materials. We talked about aluminum versus steel. Obviously, we found steel is denser but stronger. Steel will also be harder to machine. And with that, we concluded that aluminum would be best for us going forward. We've talked about what our plan is to do manufacturing, whether that's on the lathe or the CNC mill. We concluded that the CNC mill, hopefully, will be our best option with that, while still using the lathe for some things. We'll talk about that later. We also concluded that our wall thickness of about 1/8 of an inch will be the best for us, as if it's any thinner, we have the shear pins shear too quickly. And if it's any thicker, we have just more weight than we really need. All right, next slide, please. So our loads and constraints, obviously we're constrained to the diameter of the upper body tube below us and the nose cone that's above us. And then again, weight, we'd like to keep this as light as possible. Our loading conditions are the same as last year, other than this estimated 50-pound shock force. This is from the new Nosecone deployment, and this is actually a pretty conservative estimate. We think it's actually going to be much less than this. But basically, as you can see with this picture on the right, this is how we're going to be deploying, other than on the right, we're going to have the payload coupler be tethered to the nose cone, and you'll see how that affects our holes in a couple later slides. All right, next slide, please. So here's our integration of the payload coupler. Obviously, there's internal interfaces of the upper body tube and the nose cone. And then we also have the ejection systems, including the parachutes and the new nose cone ejection. External interfaces include the payload that we'd like to hold in place in the nose cone. And then we work with avionics a lot, as they have many wires and electronics that they need to put through our part. And that also changes our whole pattern. Next slide, please. So here's our concept from last year. It's a multiple part payload coupler. Basically, we've been using this because of familiarity from previous years, which comes with the ease of manufacturing. Because we're familiar with it, we know how to manufacture it very easy. But the design trade-offs are, it's more weight than we'd like it to be. And we also have to weld these parts together. And because we're making multiple parts, we use more material, and that creates a higher cost. Next slide, please. Here's our new concept. It's a unibody design made of aluminum. It's shown here at the right without the zip defender. Some design benefits here are weight and material savings, like I said. And we also only have to machine this one part, which is sort of a double-edged sword, because now we have less room for error. So if we mess up here, there's not much we can do other than just restart. And with that, we're also using more complicated machining now that we're trying to use the CNC mill. So that's another design trade-off with this new proposed unibody design. Next slide. Thank you. So here's a closer look at our proposed preliminary design. Here on the left is this whole design I was talking about, which will most likely change by the end of the year. But right now, we have this hole at the center that has our eye bolt mount. and then these rectangular pattern on the left and the right for our payload mounts. And then in the top and bottom of this picture on the left is where our CO2 Raptors will be mounted. And then in the northeast corner, we have this new hole that we're proposing is where the tether is going to be. As Brandon said, in Nosecone, where the Nosecone is ejecting, so the Nosecone doesn't fly out of the air. Okay, next slide, please. So here's our analysis. Like I said, our assumptions, same as last year, other than this 50-pound upward nose cone load. And like I said, this minimum factor of safety would come back into play here. We have it under 2.0 right now, but the reason for this is when we did Fva Analysis, we used a bulkhead of 1/4 inch thick, and we're actually planning on using a bulkhead that's 0.3 inches thick. So this should easily go above 2.0. So we're not really worried about this factor of safety at this point. Next slide, please. So here is our Fva analysis. As you can see, we're not really concerned about much of the part other than this eye bolt loading with its force, with its downward force. So much of our concern in Fva has been making sure that this center of our part is up to standard. Next slide, please. So the testing that we'll be doing on our payload coupler, we're going to be using the Instron machine in the MB department to apply a 750-pound load to the eye bolt, making sure that it can definitely handle our 500-pound load. We're also going to be having recovery testing, and you can talk to some of the recovery teams if you want to learn more about that. We will also have a payload ejection testing just to make sure that the payload does eject correctly. We're not exactly sure how that's going to work this year, but we just know we will have some testing on that. Next slide, please. All right, and so our manufacturing, definitely all dependent upon if the ME machine shop does reopen, but right now we're projecting that it will, and so with that, what we're planning on doing is having the CNC mill machine most of our part, including the forward and aft pockets and the 1/4 inch fillets. We're also going to use the lathe, but this is mostly only for the outer diameter, to shave down the outer diameter of our parts. But the big concern for us manufacturing isn't in the bulkhead, it's actually in the zip defender, with it being so thin. And so with this, we may have to rethink how we do design and or machine the zip defender. Next slide, please. All right, so here is our materials and components cost. Basically, a bulk of our cost is because of this 8-inch aluminum stock. So we're proposing about $170 this year as we're restarting our part. Yeah. And then here's our schedule. Again, all dependent upon if the ME machine shop does reopen. That's about it. I'll hand it back off to Alex.
Thanks, Eamon. I'm just going to jump into our composite coupler R&D real quick. A lot of it's really similar to what Greg talked about for the recovery coupler. We're just kind of taking the same idea that Cody Olson developed last year for Capstone and kind of adapting it for the payload coupler in the hopes that we can save some weight and increase strength as well. So diving into a little bit of the stuff that I'm not sure Greg necessarily touched on, but if you break down that bulkhead, like you said, you have the wagon wheel aluminum component in the middle. And the idea for that is it's going to be made on the water jet to cut those big pockets out for the hexel honeycomb to fit into. And then we'll cure 2 composite plates, one to go on top and one to go on bottom. and then bond it together somehow around the edges so that it all stays together in one piece and acts as a pressure sealed bulkhead. So you can see here kind of how everything's going to stack up together, including the eye bolt that's going to go through the middle. And we have our ply pattern down. We're planning on doing a 10 ply cure for the two carbon fiber sheets, the one on the top and the bottom, at 0, 90, 0, 45, negative 45, and then symmetrically flipping that. You can go to next slide, please. And so a lot of the research we've been doing so far this quarter has just been analyzing methods for how we can manufacture this, hopefully in the spring, if things open back up, kind of just as a side project. So manufacturing methods, a lot of thermal expansive properties. One of the biggest things we were having trouble figuring out was how the aluminum was going to interact with the carbon fiber, because they had different thermal properties. And if you're heating everything up and cooling it down during cures and stuff like that, you're running the risk of things breaking or warping or losing their strength and a bunch of other issues like that. And then just kind of getting into the Ansys ACP, like Greg and a couple of the other teams have talked about. So the ultimate goal for the year would be, we're going to fly our unibody aluminum bulkhead this year, assuming we launch a rocket. And we're also going to manufacture a composite coupler in the spring as an R&D project, with the hope that next year the Payload Coupler team can fly a new composite coupler. Next slide. That is all we have. Any questions from anyone? All right, next slide. And now I will hand it off to Toby in Airframes.
Thanks, Alex. I'm Toby. I'm going to be presenting the project progress report for Airframes with Sama. Next slide. So basic project overview of Airframes is that we make the body tubes of rocket. The main mechanical structure, pretty simple. And our requirements for the system as a whole is that each tube has to maintain a factor of safety of 2, but our design is going to target a factor of safety of 25, just to mitigate any errors in the layup or post-manufacturing processes. So for the current status is we're waiting to finish the manufacturing from last year, because we got about 6 of the 8 tubes done. So our design for the current rocket will not change. And so therefore, we're going to be researching 2 different projects for future iterations, mainly trying to see how big we can get the diameter of the rocket and airframes, and finalizing the design for the remote fill doors. Next slide. So our loads and constraints for the airframes is, well, our constraints is making sure we can actually build tubes we need in UW composite shops. Each tube has to carry the right loads and weights for each subsystem, and the cost of materials, new equipment we need. And so here are listed loads from all the components, drag forces, and any pressure changes. For our research and design purposes, we're kind of using loads from last year just to get the ball rolling on our design. And throughout the year, more towards spring, we're going to be updating all the weights from the sub-teams. So for integration, we're going to be integrating with fins, recovery, and the couplers team, just to make sure everything fits together. And once everything's screwed in, we got a sleek rocket. And then externally, we'll be dealing with the propulsion tanks and plumbing and bulkheads. And avionics as well, making sure certain body tubes are transparent. And so I'm going to hand it off to Sama to talk about the initial fill door design.
Thanks. So first of all, what's the function of the remote fill doors and where on the rocket will they be located? We have 2 confirmed remote fill doors in the AV bay and PRZ fuel segments of the rocket. Their role is that each door will be open before launch, and the pressure nozzles will be going through the door, and the door will be resting on those. Once the pressure tank is full, the nozzles will come off automatically and the door will shut and will need to stay shut during flight. So that's our job, to make sure that the door shuts and stays shut. We're currently looking to cut carbon fiber squares out of the body tubes and use those for the doors. We're going to have hinges to enable it to open or close, and those will be placed on the inside of the tube. So we're looking to use neodymium magnets, which will close the door once the nozzles are retracted and will keep the door closed during flight. The diagram on the left has an estimated placement of the magnets, but this will be adjusted depending on the placement of the avionics equipment. And we also have a range of possible strengths for the magnets, and the choice also depends on the avionics equipment. Another measure we're going to use to make sure that the door stays closed is an elbow catch latch, which we will 3D print or buy online. You can see an example in the diagram on the left, and that will be secured opposite the hinges. If we 3D print, we're looking at either using ABS or polycarbonate as our materials. Next slide, please. So the key constraints that our design need to fulfill are weather resistance and withstanding a pressure change of 8.5 psi upon launch. So the benefits to our proposed design are that once the remote fill nozzles come off, the door will most likely close on its own because of gravity. But we're including the neodymium magnets to make sure that the doors close and stay closed. We've also included the elbow catch latch as an extra measure to stay closed. And a bonus is that we already have the carbon fiber available left over from cutting the body tubes, so we wouldn't need to spend any money on that. There are some trade-offs though. There is a possibility that the carbon fiber won't be structurally sound for this. We're going to run Fva Analysis to investigate this, but we do have the option to 3D print the doors if the carbon fiber proves to be an issue. And another thing is that the magnets have the potential to interfere with the internal avionics equipment. This largely depends on placement and strength of the magnets, but we've been communicating with the avionics team who plan to run some tests to make sure it won't be an issue. And we're also thinking of alternative designs. The last thing is that the elbow catch latch may be too big to use. It might interfere with the remote fill nozzle. So while we're waiting on some confirmed measurements from other teams, we're also considering smaller options such as a tension ball catch latch. So although there are some trade-offs, we're investigating these and we'll be adjusting the design as needed. And I'm going to give the floor back to Toby.
Sweet. So on to the other larger research project is increasing diameter of our airframes. So for our designs and analysis, we're going to be using the same manufacturing plans and material, same carbon fiber prepreg. And so obviously the benefits would be increased area for sub-teams to, work around in. But obviously with the larger size, you're going to be using a lot more materials, and it'll also increase the weight of the overall rocket. And because we're trying to keep the weight increase minimized, we're going to try to keep it around the same 6 plies for most of the tubes, but it does lower the factor of safety pretty obviously compared to last year's design. So the extent of our research is just kind of seeing how big we can get the rocket before too many problems arise and where we can't really build it. And so currently we're analyzing a radius from 4 inches to 5.875 compared to our current one, which is about 3.98 something. And so currently sticking with 6 plies for our basic analysis. And as we continue researching it to analyze the structural integrity, we may have to increase it and mess it around for certain tubes. And the actual rigidity of the airframes needs to be researched, and the stiffness of the material at those increased sizes. But we just need to continue looking into that. And so for our analysis, we're using a MATLAB code from Julia last year that uses classical laminate theory, material properties, estimated loads, and ply orientation to kind of get an estimate of factor of safety for the required loads. So we're assuming it's a cold ambient temperature to get a conservative estimate, and the pressure changes inside the tubes will be the difference in altitude from launch to the apogee. And last year it was found that all plies being 0 degrees is the most optimized, but that was analyzed without considering moments. So that can be further looked into later on. And next slide. So after running the test with the estimated radii, we kind of looked mainly at the parachute bay because that's the tube that will be experiencing the most pressure. And so at 5.875 inches, we got a minimum factor safety of 25, which matches our constraints. And you can see the loads that we calculated to get that factor of safety. And so the current design means that at 6 plies, it can carry the weight, but we still have to look further into the actual rigidity and structure once it's made. we're hoping to do that with some Fva analysis on carbon fiber, but like most other teams, we don't really know much so far. So to the future. Next slide. So these are just the factor safeties for the other tubes that have about the same forces experiences with the pressure. And obviously it's pretty good with our factor of safety requirements being the lowest one, 130. So next slide. So when the time comes, we would like to test the larger diameter size with Instron testing, as well as the post-manufactured tubes for the current year. But to get a real good sense of how they'll perform in flight, we need to learn the Ansys structural analysis for composite structures. And the manufacturing steps would remain pretty much the exact same, where we do some prepreg layups in the composite shop, roll it up, vacuum bag it, and stick it in the oven. The main thing we would need is obviously more carbon fiber and a larger aluminum mandrel to wrap the plies around. And then after that, same deal with post-processing, where we'd be sanding, trimming, and drilling the holes to fit in with the couplers and other subsystems of the rocket. And so these are the material and components, and I know that's a lot, so before anyone yells at me, I kind of just put that there to get a sense of how much carbon fiber we need, and it's not optimized at all. It'd be a lot of waste looking at the 45 yards of carbon fiber we need. I would just kind of get in a sense of worst case scenario if we had to spend it, or realizing how much material we're using. Last year, all carbon fiber was provided by our sponsors and industry contacts, so we didn't actually have to spend a cent. So hopefully it'd be the same. And the mandrel will be, I think, a custom built or a custom request. So I have no idea how much a new mandrel at the size we need to be, but we can find that out. And for the small parts for the remote field door, they're pretty cheap that you can get from pretty much anywhere. And that would come out to about $40 tops. So crazy amount, it's not concrete. And that's our cost analysis, layup cost. We do it ourselves, so we don't really get paid or anything. So that's sweet. And we can do Instron testing in-house as well. And this is our very preliminary schedule, just because we have no idea when or if we'll be able to get back into the composite shops, but we're going to be continuing our research throughout at least until winter quarter, and developing some manufacturing plans. So in case springs look good, we can get in the shop with the ball rolling and be pretty efficient. So our next step is kind of deciding on an optimal radius of tubes if we did want to increase that further. And that would involve talking to all subsystems and trying to see which people want a larger radius and what they would do with it, and how much is just too much where it's unnecessary. And again, learning Fva analysis on composite structures will really benefit our initial designs to get a minimized weight and not go a little overboard. And then we're gonna, that was it. Questions? Sweet. So I'm gonna hand it off to Patrick Folis on fins.
All right, thank you so much, Toby. Yeah, my name is Patrick Folis. I am the project lead of your Friendly Fins team. And today we're just mainly going over the progress in research and development that was done this quarter on the Fins team. Presenting along with me, we have Joseph, Helen, Patrick, Alexander, and Alex. Quite the lineup. Let's get going. All right, so to start, why do we have fins on the rocket? We want our rocket to go straight up for its flight, minimizing the angle of attack, which is shown in blue here. And the fins provide a counter moment or a correcting force that's going to stabilize the rocket as it flies. That way it's a rocket and not a missile. The trade-off for that is these, fins are going to cause or add extra weight and also cause drag during flight. So we have all of that to consider when trying to optimize the fins for this year. Next slide, please. All right, think of this as last year's PDR crunched up into one slide here. A few things were updated for this year, however. So our fin size is going to be 24-inch on the root chord. It's only 23 in that diagram C, but that's because the fin edges are not added yet on that diagram. Essentially, the fins are made of a hex core honeycomb material, and embedded inside of that are these aluminum fin certs. That's how we bolt the fins onto the rocket. And the edges are then added after the fact with epoxy. There's a secondary cure with more carbon fiber to combine the fins and the fin can into one unit. So all of that is pretty much the same as last year, not a whole lot of updates. The fin geometry was changed a little bit. You can see our fins are now swept back slightly, and hopefully that will increase the aerodynamics of the rocket as a whole, as our analysis suggests. So this year so far, we've had a couple different research projects going on that we'll be talking about today. First, the fin edge material and manufacturing, looking at how to optimize that with new methods. An Instron testing plan, how can we test our fins and get more reliable data so we can optimize them better. And then finally, an area roll fin can, which is something that could be implemented in future years, actually changing the size of the fin can to make it more aerodynamic as the rocket flies. The overall timeline, in October, we started these projects. Of course, now we're presenting our work so far. And at the end of the quarter, we're looking to have a couple written reports for each of these projects to better document them. So starting off with the first project, the fin edge material and manufacturing. The problem we're addressing here is that last year and in previous years, 3D printing them has been problematic. Often the prints fail, and then even if they do print correctly at first, in a subsequent autoclave cure, the material often deforms and we don't get that sharp edge we want on our fins. You can see in A and B there is kind of the shape of the fin edges. The cross section is more or less a triangle for most of it. And you might think that, the fin edges are only a very small part of the fin, but when you look at it in the diagram and see there, the air sees the nose cone and really the fin edges. Those are the only surfaces it directly sees as the rocket flies. So it's really important that the leading edge of the fins is optimized to be the best in terms of aerodynamics, and then also the trailing edge too. And then finally, the last diagram in D shows what might have been the problem in terms of the deforming of the 3D printed fin edges. At certain temperatures, the thermoplastics tend to get a little rubbery and can change shape. Next slide, please. All right, so I'm going to pass it over to Joseph and Helen to talk a little bit about the materials research for this project.
Okay, thank you, Patrick. When it came to the actual material selection for the fin edge, we chose to research composites, more specifically polymer composites, due to their resistance to heat, simple manufacturing, and high strength to weight ratio. And of polymer composites, there are really two matrix materials, thermosets and thermoplastics, which both have differing mechanical properties due to the difference in bond strength between polymer chains. Thermoplastics have weak bonds between polymer chains, which result in materials maintaining the plastic mechanical properties such as like electrical insulation and impact resistance, and makes it easier to work with, but it does tend to deform under heat. Conversely, thermosets have a stronger bonds between chains due to cross-linking. And this allows the material to have a high continuous use temperature, and it remains in shape in elevated temperatures. And compared to thermoplastics, thermosets have a bit more of a complex manufacturing, but also they have more properties that are desired for the fin edge. So I'll pass it off to Helen, who did more research on the specific properties of thermosets. Next slide.
All right, so as Joseph was saying, the thermosets are generally good at offering high temperature resistance and good strength. And so what we did was look at different types of thermosets that we could use for the specific application, taking into account the temperature tolerance, the strength, and the density and the price of different materials. So I researched several types of thermosets and created different graphs and tables to basically compare the properties. And what we found was that there were several types that actually met the physical requirements that you would need to withstand the high temperatures during the curing process. So what we ended up choosing was epoxy, simply because it is easy to work with and it easily meets the requirements. And there are several different types that could be used. I'm going to pass it back to Patrick.
Yeah, so going to the applications to our rocket and to the fin edges we're going to create this year. We are currently looking to develop a reusable mold that can possibly also serve for future years. We're looking at using an epoxy-based material based on some of the research done by Joseph and Helen. It appears to be the best material for our purposes and the simplest for us to use and obtain. We need to consider that epoxy often has bubbles forming, so we'd have to vacuum treat or pressure cast during the molding process. And then also after the material has cured, we still have to add it to the rest of the fin, which would require surface prep and a secondary use of epoxy to actually attach the fin edges onto the fin. You can see the simplest mold for our purposes would be shown in A that gets the triangular shape. The only challenge with that is the 2 points shown in figure B are non-uniform cross sections just because the direction changes, and we'd have to consider how we're going to develop a mold that can accommodate that shape as well. And then finally, the next steps are finding the exact material we want to use, as well as trying to narrow down that molding process, which does have a lot of dependence on our resources available this year. We're going to also research prepping the surface for that secondary adhesion I talked about to add the fin edges onto the main fin, and cost considerations, of course, which is something Helen has done a little bit in the material, but there's also some other costs we have to nail down as well. And then I will turn it over to Alexander and Patrick to talk about the Instron testing plan area of research.
Yeah, so I'm the other Patrick on Finn's team. And the research project that Alex and I have been working on here is Instron testing. The problem we're really trying to address is the fact that we've never really had a good way of knowing the structural integrity of the fins that we put on our rocket. And so obviously we're going to be taking a look at some stresses and strains, as we all remember from mechanics and materials. Next slide, please. And so concept research, we're just diving into how we might be able to apply MIT's testing method that they sent over to try and get us to send fins to them. But due to how we manufacture our fins, we actually can't just outright steal their testing method. So instead, we're going to be looking at some other things. Particularly, one thing that we want to look into is the point of delamination within the fin. When do things actually start to pull apart? And then yielding, if that happens, depending on whether like delamination occurs before yielding, that would be something, that's obviously something we don't know. And so that's something that we look into. And then we also have a possible new concept. This is something that just came up in this last week or so on possible flight flutter monitoring during actual rocket flight. That's not something that we currently have a way of testing for without the rocket actually going off. Next slide, please. I'll pass this off to Alexander. You want to take this one?
All right. As you can see in the cross-section here, delamination is something that we might run into with our manufacturing process. So the idea of how we would test for this is we would load up a cross-section from a fin that we have manufactured into an Instron machine, and we would test basically the bending yield point where the layers start to come apart. The other thing we would test for with the same Instron machine would be our ultimate yielding point. As Patrick has said, it's very difficult, especially with the materials and manufacturing that we're using to simulate the actual breaking and yielding points. So experimental information will be the best use for us. We also touched on Flutter, as Patrick said. Just a bit of background: Flutter is when you get your fins begin to oscillate in unstable harmonic motion, and this occurs at specific speeds depending on the geometry and materials that you use for your fins. So what happens is if you were just to go through a normal turbulent flow, your fins would vibrate, but as long as you've designed them, they shouldn't come apart. However, at particular speeds, you'll introduce harmonic motion, which will increase all of the pressures that that fin experiences, which often leads to failure. It's well documented on several sounding rockets from different organizations. So generally, those are tested in a high-speed wind tunnel, which we don't have access to on campus. So the next best thing that we would be to incorporate accelerometers into one or more of our fins, so that when our rockets go up, we can basically model how our fins are oscillating alongside to our speed, and that way, if there is a failure, we know exactly at what speed it fails, and we can design around that. As far as I know, this is our testing methodology to date. If there's nothing more, I'll pass it off to our lead, Patrick.
We still have one more.
Oh, sorry.
Yeah, no, it's all good. Yeah, so essentially next steps are figuring out, just coming up with a testing setup. So we need to obviously create some sort of jig to hold the fin down during the Instron test when we do the bending. And then hopefully, if everything goes well and we can get manufacturing done sometime winter, spring, who knows, we can actually test this on some fins. Yeah, that's all.
All right, awesome. And then our last research project from this quarter is the area roll fin can. Just as we have two Patricks, we have two Alexes, and the other Alex will now introduce this project.
Great, thank you, Patrick. So the driving concept behind this is that the fins are going to be generating drag, and the idea is that by reducing the size of the fin can and sort of having it swoop in where the fins are located, we can try and reduce that drag as much as possible by keeping the cross-sectional area of the rocket as constant as we can. And so if you can kind of make out on that right-hand diagram, the little E of X is going to be the function of the curve that would be like on the body tube that the fins would sit in to reduce that area. Next slide, please. So the concept's pretty straightforward. By reducing the width of the can, we can minimize that overall cross-sectional area at the fins. And if you look at this graph here, it's graphed against the Mach number and then the drag. So the red is rocket without the area rule applied, and the blue is with the area rule applied. And as you can see, there's quite a significant difference at the transonic speed. So just before Mach 1 and after Mach 1, where there is a significant reduction in drag using the area rule. Next slide, please. And so applications to this rocket. So previous years have determined that there would not be as much gain by applying the area rule. So it does increase the complexity. There's a possibility of interfering with the propulsion system, specifically the thrust chamber, just because of the fin's locations at the back of the rocket. And it's really only effective at transonic speeds, which is only a brief portion of the flight. Next slide. And finally, next steps. So we would have to find that geometric curve for the current fin setup, run some CFD at just to sort of look at that drag and establish the effects at supersonic and subsonic speeds.
All right, so yeah, those are our current research projects. There's a lot going on the team, as you can see. The next steps for us are to try to finish up research for those projects. Some of them need to be done sooner than others, such as the fin edge manufacturing, which is pertinent to this year's rocket. The area rule fin can, on the other hand, would be something that would be done in future years. So it's a little less of a deadline for that to get done. We're going to, of course, be finishing up work orders that pertain to that slide I showed at the beginning, kind of the design process for the fins, nailing down any changes we're doing this year. And we'll begin manufacturing as facilities permit. I elected not to put too much of a detailed timeline just because so much is up in the air. But in lieu of manufacturing in person, we'll do further research on these projects and others. All right, and if there are any questions, now's the chance. All right, well, thank you for your attention. And now I'll introduce the next mini presentation here from Catherine and Ash.
Hello, I'm Catherine Butler. I'm the Nosecone Ejection lead, and I am working with parachutes also. So first off, here's a little diagram of what happens with recovery. So first we go up, and then the nose cone is ejected, and then the drogue is deployed at 1,500 feet. No, that's not right. Yes, that is right. Okay, the drogue is there from apogee to 1,500 feet, and then the parachute stage separator is triggered at 1,500 feet, and then from there on down, the main and the drogue are what's happening. So next we have the parachutes. So I'll be presenting this one. So first, just a brief description of what we're responsible for. IREC requires that we have a dual event recovery operations concept. So that means that we have a main and we have a drogue. The drogue is deployed first, and the rocket should fall under drogue between 75 and 150 feet per second. And then when the main is deployed at 1,500 feet, the rocket should fall at less than 30 feet per second. So our job is to get the rocket back down safely. And some of our goals are to maximize the coefficient of drag, to minimize weight, and to have the constructed canopy shape be as similar to the CAD model as possible. So the extent of research, we looked at a couple of different canopy shapes. On the right is kind of a diagram of what the different parts of a parachute are called. And so ram air was one of the ones we looked at, which is steerable, controllable, and has a lower coefficient of drag. And some properties of fabric that are important in this application are strength, tear resistance, elasticity, and non-permeability. Ripstop nylon is light and it stops rips, as the name would suggest, and is generally a very popular choice for parachutes. So this is just a description of what we started on last year. Let's see, the main is about 40% complete and the drogue is about 80% complete right now. So if you want to go through these pretty quickly. So there's a 7:10 ellipse ratio. So next slide. So that circle is that ellipse, and then the inner diameter is 20% of the outer diameter. And then the shroud line length is equal to the diameter, and the shroud lines are tangent to the canopy edge. And so the drogue is 6 feet in diameter and the main is 13 feet in diameter. And then we also have a rigging diagram, which will be augmented to include payload deployment. And then, so analysis. Previously, we've used OSCalc, which is a terrible, horrendous program. And one of my members has developed a new software that does basically the same thing, except it's a lot easier to work with. So importing and exporting inputs and outputs is a lot easier, and the visual interface is also a lot better. Next slide. And so here's the analysis for the drogue. Most of what you care about probably is the maximum opening shock force, which is 319 pounds. And then next slide. The main, very similar, different parameters, but has an expected opening shock force of 1,163 pounds. However, Aries is also a consideration if you're doing calculations for what your part will experience. So don't use this number, use 2,100 pounds for Aries opening shock force. Next slide. So some of the testing that we'll do, so Rainier Vista testing is mostly just for fun and to appreciate all the hard work we've done. So it's just kind of running around with the parachutes on a windy day. And being sure that they actually act like parachutes and do what they're supposed to. We're also going to do wind tunnel testing of the drogue. On the right is a picture of wind tunnel testing that we did in 2018-19. And that is some of the best data that we have about how our parachutes actually perform. And then ideally, we would like to also do a hot air balloon test with the main, which will give us a coefficient of drag for the main, and ideally measure the opening shock force of the main. We were intending to get that to happen, let's see, 2 years ago, but through a slip in communications, it fell through. But hopefully we'll get that done in the future. Next slide. So for manufacturing, the sewing machines that we'll use are located in the makerspace, the mill, and that's where all of the sewing will be done. We've already cut all the fabric for this year, but if we had to do that, that would be in the composite shop on that CNC fabric cutter, which makes our job a lot easier. And then the parachutes team will be completing all the manufacturing, so there's no cost associated with that. Next slide. So this is a more qualitative approach to a schedule. There are very few actual dates here, but it shows the order in which things have to be completed and what has to be completed before other things can be completed. So next slide. So next, we intend to start sewing as soon as winter quarter starts, as soon as I can get all of the materials onto campus. So we'll start with practicing sewing with nylon, and then finishing the main gore seams, and then finishing the rest of the sewing on the main, and then attaching all the shroud lines. All right, any questions? All right, moving on to nose cone ejection. So I am also the nose cone ejection lead. So the purpose of nose cone ejection is to deploy the drogue at apogee. We have also become responsible for, well, at least involved in deploying the payload. So I'll speak to that a little bit later. So some of our goals are to be lightweight and meet space requirements, have a fast assembly in the field with minimal cleanup, which we haven't had in previous years, and also a fast turnaround time between tests, which is something that we have also not had previously. So for integration, we're mounting, for the drogue deployment, we're mounting on the recovery coupler. The recovery coupler upper body tube and payload coupler will make a pressure vessel, and our signal to deploy will come from the recovery electronics. For the payload deployment, will be mounted on the payload coupler. The pressure vessel will be made of payload coupler and nose cone. The signal to deploy will also come from recovery electronics. And then the method of deployment, it takes a lot of integration between lots of payload projects, nose cone and payload coupler. So we've decided to use CO2 as our method of ejection. So when the CO2 canister is punctured, it will pressurize whatever area needs to be pressurized. Yeah. So now the question is how to puncture them. Next slide. And then actually the next slide after that. So there are lots of different ways to puncture these. So primarily in the past, we've used black powder, which is inside of those red parts on the right. And we have machined or bought those red parts. However, we're also exploring resin printing that part, which would greatly decrease our manufacturing time. But it's quite possible that that printed part would just explode. So we'll have to figure out about that. So benefits, we know how it works and we know how to use it. But design trade-offs, it's very difficult to clean up after each fire, and it's 3+ hours of turnaround time. So it's really not feasible to do 2 tests in one day, and it would be great if we were able to do that. Next slide. So another option that we've considered for puncturing these CO2 canisters is these small pneumatics. It would be a fast turnaround time and no cleanup, but it would require a pressurized air supply. And then the next slide. So another option is pre-puncturing the CO2 canisters, and then releasing the gas with a valve at the appropriate time. However, we really haven't looked into this much, so it needs to be explored further, and the electronics interface would be a little bit more difficult, but it has the same benefits as the pneumatic design. Next slide. So now moving on to the payload ejection. So what has pretty much been decided is that there will be 2 ejections. And first, the nose cone will eject from the payload coupler. So next slide. And so this option is to have the drone be deployed by payload in some undetermined as of yet manner. And we would not actually be involved in that. We would just use whatever system we decide on to pressurize the nose cone and eject the nose cone. Another option is for the nose cone to pull out the payload. So in this case, there would be a line between the drone and the nose cone, which would be shorter than the line between the nose cone and the payload coupler. And then next slide. So that's a little bit further along. And then the slide after that shows kind of how it would look under steady state. So the drone would not actually deploy from its little box until we were under steady state descent with the drogue. but there's still a lot of question marks. These are just some options, and we're still working on what's best. So next slide. So we haven't made a lot of decisions yet. We've decided on CO2 canisters. We don't know what puncture method we're going to do, and we don't exactly know how we're going to deploy the payload yet. Next slide. So here's some analysis for how much CO2 is necessary to eject the payload coupler from the upper body tube. So we would need 56.77 grams of CO2 at least, which gives us a factor of safety of 2. And our factor of safety due to the pressure difference would be 1.88, which is not ideal, but we think will be enough. Next slide. And then for the payload coupler nose cone ejection, the mass of CO2 required is 35.65 grams, and our factors of safety are the same. And next slide. So we have 3 types of testing. One is puncture testing. So we just want to be assured that our puncture system actually successfully punctures a CO2 canister. And then we'll do ejection testing, which is making sure that the gas is enough to actually shear the shear pins to separate whatever's being separated. And that will also be testing whether that space is a pressure vessel or enough of a pressure vessel. And then in full recovery system ground testing, we will make sure that all of the recovery systems work together in concert, and we'll determine an appropriate time delay between the 2 different ejections. Next slide. So for manufacturing, if whatever we make is aluminum, it will be manufactured by students in on-campus shops at the 8 or the ME shop. But if it's resin printed, I have a friend who has a printer that we would be able to use for that. Next slide. So we have a lot of the materials that we would need already. The only things that we would need to buy are CO2 canisters and stuff for whatever puncture system we decide to use. So there's that. Next slide. So again, this is a more of a qualitative schedule, more in reference to completing previous things, and then how long it would take to complete that step once it was started. Next slide. So next, we'll be testing the feasibility of 3D printing parts. We're going to be improving the MATLAB code that we use to calculate the massive CO2 required. We're going to choose a puncture method. We'll complete the CAD, and then order materials and hopefully start manufacturing. And any questions? All right, I will hand it off to Ash with Parachute Stage Separator.
Hi, my name is Ash, and I am the project lead for the Parachute Stage Separator. Could I get the next slide, please? So the requirements for us is we have to deploy the main parachute and withstand the shock of the shock force of drogue deployment. And this year our goals are to have a nominal deployment while minimizing weight. Could I get next slide? Constraints is we want redundant release points and to use space effectively. So neither the rocket nor any other part of the PSS can interfere with each other's deployment. And we're going to try and minimize weight. And those loading conditions are the opening shock force of the drogue, which is going to be updated to 319 pounds. And then the load during steady descent is just the weight of the rocket. With integration, we need the electronics to send the signal to the PSS to deploy. That's going to be over igniters. And rigging is going to interface with both the attachment points to the PSS. And then externally, we're going to attach to the recovery coupler eye bolt. So the design we started working on last year is this kind of body and pin bar design. And the load is distributed across kind of both the top and bottom of the body of the unit. Its benefits are it's commonly used in commercial off-the-shelf designs, and it's already been tested by other manufacturers and hobby rocketry users. And this is what we started designing and working on last year. The trade-offs are it's a little bit heavier, and with the pins having to pass through that top half of the unit, there's a slightly higher chance of binding, and there's a bit more material required. So this design looks similar. However, the load this time is distributed through the bottom half of that PSS body and the top bar, and the pins are just kind of stabilized with the top half of the PSS body. It's a little bit lighter. There's less possibility of binding since there's no holes that the pins have to pass through on the top half of the body. But the trade-offs are it's not as well tested, and we just have some basic FEA run on this so far. As for the interfacing for the rigging, we're going to use the Brummel lock splice, which allows rope to maintain over 50% of its integrity instead of using quick links. This spliced rope allows it to be lighter, saving us the entire weight of the quick link, since that just doesn't have to be used. And then the benefits of this is we started working on this last year, so we have some experience doing this. However, we will be looking into other methods of doing this as well. Next slide, please. So this year, we're going to continue manufacturing and testing the previous year's design while continuing to analyze and do FEA on this split body design to see if that would be a better option. And we'll make lines with the Brummel lock splice while working on something else, just so we have something flight ready in case we need it. And we'll use what we learned last year to improve the quality of the components, and also we'll use what we learned last year to improve the quality of the FEA and analysis. Can I get the next slide, please? So the FEA was done for the PSS unit only because it's really hard to run FEA on ropes and other kind of flexible items. So the assumptions were we used a 300-pound test load, and we fixed one side of the unit. We fixed one of the pins, and we loaded, we put the load on the other pin. And this year, unlike last year, we actually put a thin band on the pins where the load is applied to simulate kind of that interface with a rope or some other quick link where that load would actually be applied. And it passed with a 3.6 times factor of safety. Last year, we had a little bit of time to test before everything shut down. So we did Instron testing on the spliced ropes. We weren't able to test the PSS because we had an integration issue with last year's design, which has been addressed this year. But while testing the ropes, everything passed everything passed. We tested 2 to 600 pounds, which was a 2 times factor of safety. And we tested 1 to failure, which ended up failing at 1,800 pounds, which was well over anything that we needed. As for testing we want to do this year, we want to do a static load test in the Instron and verify all the machined components have an FOS of greater than 2. And we will either use the Instron machine or weights to test that. And then we want to do a unit test where we actually fire off the PSS and verify that the system functions under load as a whole. And then the full recovery system ground test. The PSS body components are aluminum, and which can be machined on the manual mill and lathe, or sorry, just the mill, by UW SARP members at the 8 or the AME shop. And the rigging, which is the spliced rope, is a 1/8 inch am steel blue line, which can be spliced together by UW SARP members using a rope splicing kit either at a shop or at home. So this year we're probably going to get a little bit more bar stock. We have some in this SARP room, but because of that R&D project, we should get a little bit more just so we can have it to make those experimental PSS body units. And we're going to reuse the aluminum flat bar for the little top piece of the PSS from last year. And 1/8 inch am steel rope and a little rope splicing kit so we can do the rigging portion of that. The schedule is I want to start machining at the 8 if it's still open at the beginning of winter quarter. And I'm giving a generous timeline just in case other people need the shop before us or it's harder to get scheduled. But it takes about 5 hours for each unit to be machined. So if we want 2 to test and 1 for a flight unit, it's about 15 hours of machining total. Next steps are going to be continue updating the CAD and rerunning FEA, increase accuracy before manufacturing, and continue working on the new design, which enable manufacturing when the shop's open and all that. Also create standard operating procedures for testing after, so we can start testing immediately after manufacturing is complete, and look into other splice and rope possibilities to test. On this slide, I just have a few pictures of the PSS FEA and a little bit of an updated kind of exploded CAD view. This is one of the things I was talking about updating the CAD and FEA is because in the CAD we had up until last week, we didn't really have a good model of this top bar design. So it was kind of just modeled as a block of aluminum sitting on top. So getting this updated CAD and, you know, continuing to improve accuracy is something that we're going to be doing in the near future. Can I get the next slide, please? Any questions?
All right, if no questions, that is all we have today. Thank you everyone for sticking around. I know we passed our 8 o'clock expected finish by a little bit, but appreciate everyone sticking around for this entire presentation. Everyone is of course free to leave at this point, but the leads and I will stick around a little longer in case there are any extra questions. Thank you to everyone who presented. Awesome job. This was a really nice presentation. So as I said, you all are free to leave, but we will stick around a little longer in case there are any questions.
And Zach, thank you for flipping slides for the last 2 hours. It must have been very strenuous.
Oh, my pleasure. I enjoyed it.
Is that 174 slides?
178.
Wow. Hero we need, not the hero we deserve. Okay, I had a couple questions, but I will probably just be like messaging in your channels.
Sure.
Specifics.